here at the notes for section 10.3, which is the Taylor's theorem. So approximating a function with Taylor polynomial and so on and so forth, their objectives. Okay, so Taylor polynomial, find a Taylor polynomial that will serve as an adequate substitute for sine x on the interval negative pi to positive pi. So first thing is to adequate, we need to define adequate. So we'll say it's within 0.001. So what we actually need to do is we need to figure out so there's our Taylor polynomial. This difference has to be less than 0.001. Now at pi, sine is 0, so what I'm going to do is I'm going to use the Taylor polynomial or the Maclaurin series, sorry, for sine and evaluate it at pi, because in that case this becomes 0, and check to see whether this gets down to that value. So for sine, the approximation is x plus x cubed over 3 factorial plus x to the 5th, minus, plus 5 factorial minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial plus blah, 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 blah. And we just keep on going out. So notice that the exponents are all odd and the numbers on the bottom are all the factorials. We just need to figure out how far we need to go to get the value less than that. So, for example, we can't just use the first term because then it's just pi. So let's try the second term. So that gives us pi minus pi cubed divided by 3 factorial. Which is negative, which is 2 something. So then we just add on another term, plus pi to the 5th divided by 5 factorial. So that's 0.5. So next term minus pi to the 7th divided by 7 factorial. So still too small. So plus pi to the 9th divided by 9 factorial. Oops. Closer, that's 0.006. So minus pi to the 11th divided by 11 factorial. So that's 0.0004. So we're getting closer. It's probably the next one. So plus pi to the 13th divided by 13 factorial. And there we go. So that is, so we need the 13th order polynomial, which is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial minus x to the 11th over 11 factorial plus x to the 13th over 13 factorial, because this comes out to be just that, which is just enough for us. That's 0.00005, or 2, I mean. So there you go. Okay, so in practical terms, I would like to use a Taylor polynomial to approximate functions over the interval of convergence. Since the error results from truncating the series down to a polynomial, because this would theoretically go on forever, we just cut it off once we're close enough. It's referred to as a truncation error. So here it says find a formula for the truncation error if you use 1 plus x squared plus x to the 4th plus x to the 6th to approximate 1 over 1 minus x squared over the interval -1 to +1. Okay, so let's see here. So the truncation error is the part that we left off, which would be x to the 8th, look at the pattern, plus x to the 10th, plus x to the, x to the 12th, plus so on and so forth, all the way up to x to the 2n. Notice it always doubles. 0th, first term, second term, third term. The exponent is twice. So that is our truncation error. Now, so this is a geometric series. Each term is x squared times the previous one. So to find what this converges to, it's the first term divided by 1 minus the value for r, which is x squared. So this is a formula for the truncation error of this, given that. So that's A, that's R. A is the first term in the list. R is the ratio between sequential terms. So x squared, and the formula is A over 1 minus R is what you converge to. So there you go. So that's your error. Instead of doing all the addition, since it's a geometric, we can just use the formula for it. Okay, so we have alternating series error bound. So suppose the terms of series have the following three properties. The terms alternate in sign, so positive, negative. So it's like our sine function before. The terms decrease in absolute value, meaning they get closer to zero. Whether they're positive or negative doesn't matter. The absolute value just means closer to zero. The terms approach zero as a limit, so they'll eventually reach zero. The truncation error after n terms is less than the absolute value of the n plus first, or n plus 1th term. That should actually be up in the exponent. Okay, so the remainder. So if f has derivatives of all orders on an open interval I containing a, then for each positive integer n and for each x in the interval I, f of x equals blah, 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 so however far you want to go, plus this remainder term, where r and n is the next term for some c between a and x. Okay, so the first equation is Taylor's formula. The function Rn is the remainder of order n, or the error term, if you approximate with Pn. It is also called Lagrange point, or a form of the remainder. The bounds of Rn using this are Lagrange error bounds. So prove that the series, blah, 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 converges to sine x for all real x. So let's see here. So we need to figure out what happens to this. So we need to work out, whoops, off the screen, r of n of x as n goes to infinity. So as we let our numbers get much larger. So r of n, or Rn of x, is equal to, let's see here, f of n plus 1, the n plus 1th derivative at some value c, over n plus 1 factorial times x minus 0 to the n plus 1. So, right. So let's see here. What can we do next? So what I can do is I can measure the absolute value of this stuff. Because this is the derivative, and we're talking about the sine function, this will stay between 1 and negative 1. So this factorial term is always positive, so I can rewrite it like this. And then this guy just becomes the absolute value of x to the n plus 1, because the minus 0 doesn't matter. So this will be 1 up top at most. So we get this. Okay. So as we let n go to infinity, let's see here. If you look at how these compare, this function as n goes to infinity, this will grow much faster than this, so this will eventually reach 0. So it converges because our limit is 0. Okay, so bounding the remainder. So there are positive constants m and r such that this, I think I'm missing an absolute value bar somewhere. Yeah, should be one here. For all t between a and x, and the remainder in Taylor's theorem satisfies this inequality. If these conditions hold for every n, and all the other conditions of Taylor's theorem are satisfied by f, then the series converges to f of x. Okay, so the Maclaurin series for e to the 7x is given by this. Proof that it converges to e to the 7x for all x. So our f of t is given by e to the 7t. So that's that part. So I can work out what the n plus 1th derivative is, because what happens is every time I take a derivative, a 7 comes out front because of how e works. So 7 to the n plus 1 is the first derivative, have a 7, so on and so forth, and then e to the 7t. So there's that. Okay, and then so let's see here. So there's our m. It's going to be e to the 7x. So what I can then say is that f m plus 1 of t less than or equal to m times 7 to the n plus 1, because that's the ratio between terms. If I divide this guy by this guy, that's how I get r. Okay. Let's see, what else can I do? So this becomes 7 to the n plus 1 e to the 7t less than or equal to e to the 7x times 7 to the n plus 1. So this is a true statement, just written out of the other order, or equal to. So converges. Okay, so analyzing the truncation error. So a geometric series error, if you happen to be truncating a convergent geometric series after n terms, the remainder forms a geometric series. The error can be found exactly by using the formula with the first term, a n plus 1, and the ratio r. Thus, the error equals the next term that you're not using divided by 1 minus r. So this is no need to approximate the sum, since you can just do it exactly if you know the first term and the r value. Alternating series error bound, truncating series of an that is alternating sign with terms that decrease in absolute value with limit 0, then there's a convenient upper bound on the error at the absolute value of the first discarded term. Thus, the series is truncated after n terms. The error is equal to the absolute value of a to the n plus 1. Notice this is not a form of the error itself, which must be considerably smaller than the bound. Lagrange gives you this. Any Taylor series after n terms, then the exact error is given by this for some c between x and a. When using nth degree Taylor polynomial about approximate for some f of x, you'll know n, a, and x, but not c. However, you can still bound the error if you can find an upper bound for c between. So we know what that was. We did the sign, like the biggest that this was for the sine function was 1. So we know the error has to be less than or equal to some value. All right, so suppose we use the first two terms in the Maclaurin series for ln of 1 plus x to approximate f of 0.1. Find a bound on the error using a, the alternating series error bound, and b, the Lagrange. Okay. So let's see here. First two terms. So we need, so this would be x minus x squared over 2. So f of 0.1 is approximately 0.1 minus 0.1 squared over 2, which is about 0.095. Okay, so the Maclaurin series satisfies the criteria for the alternating series error bound. So the error is less than the magnitude of the third term. So for A, alternating series error bound, so the error is going to be equal to, sorry, not equal to, less than there a typo up above? Yeah, this should not be an equal sign. It should be less than sign. Okay, so there's less than the one term I didn't use, so the term that I did not use would be 0.0 or 0.1 cubed over 3. So that would be, error is less than that. So the error is less than, and if I work this out, this becomes 3.3 times 10 to the negative 4th. Okay, so let's see here. So for B, the one I didn't use, so Lagrange, so I went up 2 terms, so I need the third derivative. That's some value C. So if I take the third derivative of the natural log of that, I end up at C would be 2 times 1 plus C to the negative 3. Okay, so let's see here. Our error is equal to that times x minus a to the n plus 1 over n plus 1 factorial on the absolute value of all of this fun stuff. So this is going to equal so we did Maclaurin series, our a value is 0. So we've got, and our x value, so we got 2, 1 plus c to the negative 3. This is going to be 0.1 minus 0 to the third, because that's the first term we didn't n plus, we went 2 terms, so our n is 2. And on the bottom, we'll have 3 factorial. So let's see here, this comes out to be .1 cubed, that's that stuff, over, let's see, that's 6, so it's going to be, no, just 3, sorry. Because that's going to be 3 times 2 times 1, that the 2 and the 1 will cancel with that, and then 1 plus c to the negative 3. Okay. So since c has to be between a and x, that's between 0 and 0.1, so, and the denominator is greater than 3, so the error is equal to, so this guy just goes away, becomes 0, so 0.1 cubed over 3, which once again was the same thing we got before, 3.3 times 10 to the negative 4th. Oh, there you go. Fun stuff. Okay. Example 6. Suppose the second order for f of x by x equals 2 is used approximation. And suppose that the third derivative, a value of third derivative is less than 2/3 for all x's in the intervals 2 to 2.5. Show that this for all x's in the interval. Okay, so let's see here. So the absolute value of f of x, the function, minus p2 of x is equal to the error, which is equal to the absolute value of our third derivative at c, and then we got x minus a, which is 2, cubed over 3 factorial. So n is 2. So this is our n value right here, 2. Okay, so that, now if we fill our numbers in, we know that this has to be less than, this is less than 2/3, x minus, so x is here, so 2.5 minus 2 cubed over 3 factorial. So we get so we get 2.3 over 48 is less than 0.05, which is what we were trying to prove. And that brings us to the end of the section.